Hi everybody, welcome back to the Feynman technique. So this is going to be a very long video. We're going to be solving this integral and we are going to be using only concepts that can be understood by someone with a background in calculus BC. Um, the only other thing you're going to need to know is Euler's formula, which is not that big a deal. If you don't know Euler's formula, go ahead and look it up because we will be using it. Um, But anyway, let's go ahead and get started. And I'm going to be we are going to be using some formulas, but I'm going to be deriving them in this video using nothing but things that people with a calculus BC background would be able to follow. So the first thing we're going to do is we're going to rewrite this using the exponential form of sine hyperbolic. So the hyperbolic sine function is just this. It's e to the x minus e to the negative x over 2. That's the sine hyperbolic function. So we're going to bring that 2 right outside the integral. So now we have this. All right, so next step. Let's let x equal natural log u. So if we let x equal natural log u, we get dx equaling 1 over u du. All right, so let's rewrite this. Well, infinity is the natural log of infinity, and 0 is the natural log of 1. And then this will become natural log u cubed, and then e to the natural log u is just u. E to the negative natural log u is just 1 over u. And our dx becomes 1 over u du. All right, we're going to bring this u inside the denominator here. We'll paste it here, and we'll paste it here. All right, of course, this is u squared, and this, oh, sorry, u squared, and this just becomes 1. Great. Okay, so now let's do u is equal to 1 over w. So u equals 1 over w. That implies that du is equal to negative 1 over w squared dw. All right, so what does that mean? I is equal to, all right, u is 1 over w, so we get 1 over w. This becomes u to the negative 2. 1 over infinity is 0, 1 over 1 is 1, and du is negative, sorry, this should be a w, negative 1 over w squared dw. All right, next. Well, let's just keep going with this. Let's use this negative sign to switch the bounds of integration. Let's use the properties of logarithms to just call this a negative natural log w. And then let's see, this is basically negative 1. So we can bring that outside as a negative 1 cubed, which is just a negative sign right there. So we have this. Let's see, this w squared will distribute inside the denominator. This simplifies to 1. This goes away. And we can bring, let's use this w, this negative sign, to switch this to w squared minus 1. W squared minus 1. All right, I hope you followed that. All right, so now let's look. We have I is equal to this, and I is equal to this. So we have I here and I here. Well, that means that 2I is equal to this plus this. Okay, dividing both sides by 2, we get this. I is equal to this. All right, I'm going to, and now we can combine these two. One goes from 1 to infinity, and the other goes from 0 to 1. And not including the dummy variable, um, they're the exact same integrand. So we can say now that I is equal to the integral from 0 to infinity of natural log x cubed over u squared minus 1 du. Sorry, dx. I don't know why I put u there. All right. Okay, so and now we're stuck unless we develop a formula. So let's do that. Let's define some function of a new parameter t equal to the integral from 0 to infinity of let's call it x to the t over x squared minus 1 dx. And I just want to show you really quick. This is kind of a wonky function. It's basically it's undefined at a lot of places. Um, undefined, yeah, we keep getting undefined, undefined, undefined. So, and the reason for that is this integral doesn't behave. This function does not behave nicely. However, this one does. We're going to add a minus 1 in there. And now the function behaves nicely. It converges for the absolute value of t greater than, or I'm sorry, less than 1. You can see if we trace this down here. Yeah. So that converges for the absolute value of the real part of t less than 1. Okay. Well, let's take 3 derivatives of this thing. All right, so let's take f prime of t, and now we're going to be using the Leibniz rule for differentiation under the integral sign. I'm not going to be explaining what that formula is. It's the cornerstone of this entire channel. So hopefully you know what that is. If not, it's one of my very first videos where I go over how to use it. But anyway, we're going to be taking the derivative of f of t directly using the Leibniz rule. So f prime of t is going to be equal to the derivative with respect to t of this. And the Leibniz rule says that you can bring this derivative inside as a partial. All right, now taking the partial with respect to t of this, the only thing that depends on t is literally this. So this part is going to drop out, and this is going to be held constant. So we just take the derivative with respect to t of that part, which is x to the t times the natural log of the base, which in this case is x. Okay. Well, what happens if we take another derivative? We get this. Following the same idea, we're just going to get a natural log squared x. And then f triple prime of t is equal to this. Natural log cubed x, which is exactly what, well, not exactly, but this is almost I, except when t is equal to 0. So you'll notice if we plug in t is equal to 0, this whole part is going to go away and we'll have I. So what we can say is that f triple prime at at 0 is equal to I, and you can see the numbers match up. So f triple prime at 0 is indeed I, so we'll say that's equal to I. Okay. And I'm going to erase this just to keep it a little... No, you know what? I'll keep it. It's an important step. Okay, so now we're going to need to figure out... We're going to need to find a closed form expression for this, and that's going to be the toughest part of this entire video. I've already went over how to derive a closed form expression for this, but I want to do it again as part of this video, so we're going to do that. So let's ignore this minus 1. We want to find a closed form expression for some integral from 0 to infinity of let's see, x to the t over x squared, and then we're just going to say plus a squared. Okay. Um, and then you'll see if we evaluated this at the point a is equal to I, we would have the first part of this integral right here, which is all we really need, because the second part is actually a constant because it's just x terms integrated with respect to x. It is a divergent constant, but it is constant. It's not going to affect the rate of change of f of t. So this is the only part we really need. So let's manipulate this. Well, actually, let's leave it alone for now. In fact, I don't even know why I showed it. This is what we really want to do. Okay, so we're going to be developing a formula g of t equal integral 0 to infinity of 1 over x to the t plus 1 dx. All right, to start, this is what we're going to do. We're going to just break out some trigonometry really quick. All right, I hope you would all agree that sine of x is equal to 2 sine of x over 2 cosine x over 2, right? Okay. So from there, we can say this. Sine of x over 2 is equal to 2 sine of x over 4 times cosine x over 4. And from here, we can say that cosine x over 4 is equal to 2 sine x over 8 times cosine x over 8. And we'll do one more just to really reinforce what's going on here. From here, we can say this. Okay. Now let's go back to this expression right here, and we'll plug in what we know sine of x is. Sine of x over 2. Sine of x over 2 is this. So we're just going to put it right here. And this is actually 2 times 2, and we're going to write that as 2 squared. All right. And now we also know what sine of x over 4 is. It's this. So we can replace that right here. And this is going to be now a 2 cubed. Oh, but look, we also know what sine of x over 8 is. Sine x over 8 is this. And the pattern continues. We could continue doing this. This is now 2 to the 4th. And we'll stop there and develop a pattern. Okay, so let's just stop there. Let's see, and now we're going to write this as sine of x over 2 to the 4th. All right, and then we're going to divide both sides of the equation like this. Okay. So, let's rearrange these. I'm going to put the cosine x over 2 first. I'm going to put the cosine x over 4 second, cosine x over 8 third. And you'll note, and now let's put this all in terms of n. Okay, so our n is 4. So let's put an n here and an n here. And this is, now rewriting this, we're going to have to break out a new concept. It's not much different than the infinite sum concept. You just start at some index and end at some other index. And you'll notice that we have the product of a bunch of cosine functions. And the only way they're changing is the inside of the cosine function, its denominator is just 2 to the something power, some integer. So let's rewrite this as, and I'm just gonna push this over a little bit. And we're gonna say this is the product as some k goes from, let's see, how many terms do we have? We have 1, 2, 3, 4. That corresponds to our n. So we have 1 to n terms, right? However many, whatever our n is, we will go that many terms. And what we're multiplying together is cosine of x over 2 to the n. You'll see for n, and you can check this out, for n is equal to 4, we get this. Oh, and I made a critical mistake here. This is actually 2 to the k, because it's actually k going from 1 to some n value. And now I'd just like to show you that this actually does work. All right, so what we're going to do is we're going to copy this down here, and we're going to also copy this right underneath it. And then we're going to pick an n. Okay. Let's get rid of this one. Let's get rid of our... Okay, so now it's just these two functions being graphed, and I want to show you that they are in fact the same function, no matter what integer n we pick. So they are the same function. Let's just go ahead and pick 10. All right, so this is, yes, that is the same function. So that is true. This right here is true. Okay. Well, how does that help us? It doesn't help us much yet, but let's do something else. So I hope you would all agree that the integral from 0 to infinity of 1 over x squared plus t squared dx is equal to pi over 2t. And I'm not going to go through how to do that integration. That's fairly simple stuff, but I'll show you that it is true. What I'll do is I'll create a g of t equal to pi over 2t, and then we'll create an h of t equal to this, and they are going to match for t greater than 0. All right, let's bring out our graph again, and you can see they do. There's the purple one, there's the blue one, and they overlap right here. Okay, and those are the only values of t we're going to be interested in anyway, so it's all good. All right. Okay, so now we're going to start manipulating this thing. So the first thing I'd like to do is let's let t squared equal I. Well, using Euler's formula, I is actually equal to e to the I pi over 2. So this implies that t is equal to e to the I pi over 4. All right. So let's copy this down here and plug that in. We have t squared is equal to I. I is the imaginary unit. It just has the property that I squared is negative 1. All right. And then let's rewrite this as t to the negative 1. But what is our t? Our t is e to the I pi over 4. So we get e to the negative I pi over 4. All right, so that's true. Now, using Euler's formula again, we can see that this is equal to pi over 4 times cosine of negative pi over 4 plus I sine of negative pi over 4. And let's get rid of this graph because we don't need it. That way you can see more of the work I'm doing. Okay. All right, so now we have that. Now let's go back over to here and let's manipulate this a little bit. Let's multiply the top and the bottom by x squared minus I. All right, on the bottom, well, we're going to get times x squared minus I. Now, this is going to evaluate to x squared minus, or x to the fourth minus I squared. I squared is defined to be -1, so minus I squared is just 1. So this denominator here becomes x to the fourth plus 1. And now we can take the real and imaginary parts of both sides of this equation, and in fact I'm going to eliminate that middleman there and use the fact that cosine negative pi over 4 is just cosine pi over 4, and sine negative pi over 4 is negative sine pi over 4. So we'll bring this out, and now we're going to match up the imaginary sides on both, the imaginary parts on both sides. And what this is going to mean, what we figure out by doing that, is that the integral from 0 to infinity of 1 over x to the fourth plus 1 dx is equal to pi over 2. This is pi over 2, sorry. Pi over 2 times sine of pi over 4. And let's just paste both those values down here so you can actually see that being true. See, it is. Okay. So now we have that. All right. Well, now let's figure out another integral. Let's take an integral 0 to infinity of 1 over x to the fourth plus t to the fourth dx. All right. Well, that is going to be equal to, all we're going to do is we're going to factor out a t to the fourth, or multiply the top and the bottom by 1 over t to the fourth. So 1 over t to the fourth, and then this is going to give us x to the fourth over t to the fourth, and t to the fourth over t to the fourth is 1. And then, I'm not going to show the substitution, but let's just bring x to x over t, or x to tx. And what we would get is this is 1 over t to the fourth times the integral from 0 to infinity of 1 over x to the fourth plus 1 times our new differential, which is t dx. So we have t dx. And this t is going to cancel one of our t's down here. So it's 1 over 3 integral from 0 to infinity, or 1 over t cubed integral 0 to infinity of 1 over x to the fourth plus 1 dx. And let's get rid of that middleman right there. So this is true, and don't forget, we know the value of that definite integral. That is just this. All right. So now let's let t to the fourth, again, we're going to let t to the fourth equal I. All right. Which is equal to e to the I pi over 2. And that implies that t is equal to e to the I pi over 8. All right. So now let's use that substitution. Well, we define t to the fourth to be equal to I. And we define t, which led to t being equal to e to the I pi over 8. Let's rewrite this as a t to the negative 3. T to the negative 3. And then our t becomes e to the I pi over 8, so we get e to the negative 3i pi over 8. All right. Well, that is equal to, again, using Euler's formula, this part right here is going to be cosine negative 3 pi over 8 plus I sine negative 3 pi over 8. We'll bring out this negative again, just like we did before, and this just goes away because of cosine's evenness. All right, and we're going to perform a similar trick over here. We're going to multiply by x to the fourth minus I on top and bottom. That's going to give us an x to the eighth plus 1 on the bottom there. And then matching the imaginary parts gives us integral 0 to infinity of 1 over x to the eighth plus 1 dx being equal to pi over 2 times sine of pi over 4 times sine of 3 pi over 8. And of course, I'm going to show you that that's actually true. So let's paste this value right here. We get that, and then let's paste this integral here, and we get the exact same thing. Okay, so that's true. Now we can continue this process indefinitely. Let's go one more. All right, if we follow the pattern, what's going to happen is that we're going to get an x to the 16th here, and we're going to add an additional sine term. Now let's notice the pattern. The coefficient in front of pi is always 1 less than half the value of the denominator. Okay, so this next term is going to be, well, and the denominator's double every time. So we get 16. 1/2 of that is going to be 8 minus 1 is 7. Okay. Now let's convert this into terms involving n. Okay. Let's see. This isn't turning out how I wanted it to. But let's keep going. Yeah, let's just keep going. It's going to lead to the right place. So, let's define this integral from 0 to infinity of 1 over x to the 2 to the n power plus 1 dx. Well, that's equal to pi over 2 times the product as, let's see, we have four terms in our original one. So, and where does our index start? It starts at, let's see, the thing in the denominator is 4. So we're going to have to start our k, it's actually going to be k, at 2. And we're going to be going up to n. And what we're going to have inside is a sine of pi over 2 to the k power. All right, now let's see if this is true. All right, that's an n equals 1 term, and then let's just see if this actually matches up. Okay, it does. 2 matches, 3 match. Ooh, 3 does not match. What have I done? Oh, okay. I hope some of you realize this. This part on top, we forgot to realize, or I forgot to put that it's actually varying. Don't forget, we said the thing on top is always 1 less than 1/2 of the denominator. So 2 to the k divided by 2. All right, so that should be correct. So let's copy these down and make sure that that's actually true. Okay. So for n is equal to 1, we get the right thing. Let's bring n up to 5. Yeah, we get the right thing. N up to 17. Yeah. 16, 15, 14, 13. Yeah, we get the right thing. Okay. So now this is true. All right. Now let's manipulate this a little bit. Let's bring this pi inside. Okay, so this is going to be minus pi. Okay, and now let's make this two separate fractions. All right, so this last one here is just going to be pi, and then we're just going to have this. Okay, let's divide the top and the bottom of this one by 2 to the k. So we get a 1 here and a 1 here, which we don't need, and this is just pi over 2. Okay. Um, Now let's use sine theta, or sine of pi over 2 minus theta equals cosine theta, to imply that sine of pi over 2 minus, now this is our theta, is going to be equal to cosine of pi over 2 to the k. All right, so this expression right here is just this. All right, great. Let's check this. Let's check this before we go any further. Plug in some values for n, 2, 3, 4, 5, 6. Yeah, looks good. Okay. So this is true. All right, well, that's pretty close to this, isn't it? Pretty close. Let's copy this down here, just so we can compare them a little bit and see what we're going to need to do to manipulate these to kind of be equal. Well, let's see. Our index is starting somewhere different in these places. So we either need to move this index down to k is equal to 1, or move this index up. So what are we going to do? Would we rather subtract a term and then multiply it back again? Let's try that. I'm actually not sure what the correct thing to do is here. Let's start our k at 2. What that did, what that did was it basically subtracted the k is equal to 1 term. In other words, I'm sorry, it removed a multiplication of cosine x over 2 to the 1. So we need to put it back. So we have cosine of x over 2. All right. So that should be true. And let's check it. We're gonna check it. All right. Oh, sorry. Hold on. All right, so this is a function of x, and this is a function of x, and we just want to make sure that we're on the right track. So let's plug in a value for n. All right. Let me scroll up here and get rid of all the graphs we don't need. Okay. So this is n equals 1. You can see the graphs match up. N equals 2. They still match up. 3. They match up. Yeah, so we did the right thing. Okay. So this here is true. This right here. Okay, now let's see. Cosine x over 2. Let's see. Well, actually, let's rewrite sine x. Don't forget, from the very beginning, when we were just getting started up here, I think I erased it. Yeah, but we know what it is. We know what sine of x. Sine x can be written as 2 cosine x over 2 times sine of x over 2. That's no problem. Okay, now we can divide both sides by cosine x over 2. Great. Okay, and again, we're going to check this because I really, really, really do not want to make any mistakes and have to go back and fix it later. So there's our 1, there's our 2, 3. Yeah, these both match up. They all match. I'll show you. It matches at 3. It matches at 6. Yeah. Okay. So that's 100% correct. All right, so we're right here now. So this is true. All right. And now let's take a look. These are almost exactly the same, except, oh dear. Nope, nope, we're good. Okay, so now let's manipulate this again. If this is true for all x, it's going to be true for x is equal to pi. Okay. Um, so let's just plug in pi. So this is true. Pi, and then pi, right? That's 100% true. Okay, and now this is almost the same as this. All we need to do is multiply both sides of the equation by pi over 2. So let's do that. Pi over 2. And now this is equal to this, and this is equal to this. So now we have this equation. And of course, let's check it. We're going to copy this down here, and we're going to copy this down here, and we're going to plug in various values for n. Okay. And you can see it works. And we don't even need to use integer values for n. Yeah. Matching up perfectly. Okay. Now comes kind of a wishy-washy part. We're going to replace 2 to the n with just some other variable t. Okay, and we're justified in doing this because 2 to the n grows and shrinks smoothly as n grows and shrinks smoothly. Therefore, this thing does the same. Therefore, this thing does the same. Therefore, this thing does the same. Therefore, the integral of that thing does the exact same thing. So it's increasing and decreasing smoothly based on n. So we can just replace 2 to the n with some other variable t. So let's do that. 2 to the n now becomes a t. T. Oh, and by the way, what's sine pi over 2? It's just 1. Okay, this cancels this. And we have a pi here. And that's what we were trying to show. And I'll switch it around. So integral 0 to infinity of 1 over x to the t plus 1 dx is equal to pi over t sine of pi over t. And it's usually written as pi over t times cosecant of pi over t. But we're going to leave it like this. I like this better. All right. So don't forget, that's exactly, we were trying to find a formula for that, weren't we? So we can get rid of all this other work and just copy this right up here and move on from there. All right, so we're going to delete the rest of the stuff underneath this. Okay. Okay. Well, let's see. What do we want to use this integral to find? What are we trying to do? We need to find a closed form expression for this. So let's figure out what this expression would be equal to. Integral 0 to infinity of x to the t over x squared plus a squared dx. Let's try to find a closed form expression for that by using this fact. All right. Let's see. What's really messing us up in this is the fact that in this integral, we have a constant on top. And in this one, we have a variable with respect to our variable of integration. So that's no good. Now, what I'm going to do is kind of a tricky substitution. Instead of, just trying to find some u to set equal to some function of x, to make it work out, what I'm going to do is I'm going to force it to work out right away. We're going to say that x to the t dx, that's this part right here, x to the t dx, and we're going to say that that's going to work out to be du. Okay? And from there, all we have to do is integrate both sides. Integrate and integrate. All right. Well, that means that, let's see, if we integrate x to the t dx, we're going to get x to the t plus 1 over t plus 1 is equal to u. All right. Well, let's figure out what our x is in terms of u. So I'll just copy this. Okay, so that's equal to u. And now we're going to multiply both sides by t plus 1. All right, good. And now we're going to raise both sides to the 1 over t plus 1 power. And that was to isolate this x right here. So we're going to get u to the 1 over t plus 1 times t plus 1 to the 1 over t plus 1. All right. And of course, this, we made this so that it would simply be x. Great. So now let's put this into here. Let's use that substitution. All right. So x to the t dx was specifically tailor-made to be du. Oh, but what about our bounds of integration? They're not going to change. Okay, they're not going to change. See, if x is infinity, then the only thing that would make it infinity is if u was equal to infinity. And if x is equal to 0, the only thing that would make it 0 was, well, t is equal to -1 would make it 0. But that's not one of our variables of integration. So the only thing that would make it 0 is 0. So our bounds of integration do not change. All right. But now, what about our x squared? What does that become? It's going to become this whole thing squared. Okay. So, oops. This whole thing squared. Oh, there it is. And if we square it, we get this. And our du, oh, well, actually, that's it, right? That's all it is. Okay. Let's see. Let's rewrite this a little bit more. Let's make sure that this expression and this expression actually give you the same thing for various values of t and a. All right, so let's let t equal 1/2, and we'll let a equal, well, let's make it over pi to the e, just to make it really gross, and we'll make our a equal to 10. All right, and you can see those two expressions do match up. This one and this one equal the same thing. So that is a valid transformation. And now what should we do? Okay, what we're going to do is we're going to multiply the top and the bottom by 1 over a squared. All right, so multiplying the bottom by 1 over a squared, that's going to turn this into a plus 1, and then we're going to have over a squared. Okay. I would like this entire expression to be something all raised to the... Well, first of all, let's make this all something squared. You'll notice that every single one of these is something squared. So we're just going to create one expression and square the entire thing. Now this is just 1, this is just 1, and now this is just a. Okay, now we have raised to the, every single one of the things on top here is raised to the 1 over t plus 1 power. So I want the thing that's in the denominator to also be raised to the 1 over t plus 1 power. Okay, well, the only way to keep it the same would be to raise it to the t plus 1 power and then raise it to the 1 over t plus 1 power. And now we have the exact same thing. And now we can actually create another parentheses here and say that, let's see, let me think. Okay. Yeah, so we can get rid of all this and just raise the entire expression to the 1 over t plus 1 power, which is going to just put a t plus 1 right here. Okay, let's check. Let's check. So we have this expression and we have this expression. Let's make sure they're equal. Let's let t equal 1 over 4 to the 2 pi e. How about just 2e? And we'll just say that this is pi 2. Okay. And let's let our a equal e. All right. Now let's make sure that, yeah, these expressions do, in fact, match. So we are good. This expression right here is equal to this, is equal to this. So we have done the correct thing. All right. Great. Does this help us? Let's see. Okay, so I had to pause the video and back up. Because I got a little confused. It's a very difficult problem. Let's start over from here. So, our x to the t dx was defined to be du. So, there we go. And our x is this. Our bounds of integration don't change. Our x is this. And then it's squared. Okay. So now let's divide by a squared on top and bottom. Divided by a squared, and then on the top, and then bring it out, we get 1 over a squared. Of course, this can just be brought right inside of this as just an over a. So we'll just put over a. And this is, of course, 1. All right, and now we want to express this as something raised to the 1 over t plus 1 power. All right, so that's going to be a to the t plus 1 power raised to the 1 over t plus 1 power. And then you'll notice every single one of these things is raised to the 1 over t plus 1 power, so we can get rid of all those exponents and bring it right outside. So 2 over t plus 1. Okay. And now, one final substitution. We're going to let this equal w. All right, so equals w. Well, this implies that, well, let's just copy it. And let's multiply by this and divide by this. And of course, this is going to imply that du is equal to, let's see, this w will come out front. This dw. And let's clean it. We'll leave it like that. All right, so let's copy this down and perform our substitution. Okay, bounds of integration, again, they're not going to change, as they often don't when you're using bounds of integration from 0 to infinity. This was defined to be w, and our du is now this. And this is, of course, a constant, which can be brought right outside. Okay, now let's check it. We need to make sure that this is in fact equal to this. So let's plug in a 1/2 and then maybe a 1.67, and we'll make this 1 over e. Okay, they do. I mean, they pretty much match. Yeah, this and this are pretty much the same thing. Okay, I mean, not pretty much they are. This is just it evaluates it numerically, so it makes a little bit of error at the very tail end of the decimal. But they are the same thing. Okay, so let's get rid of that, and then just paste up here that this is equal to this. And now let's clean up. All right. Get rid of that parentheses, get rid of this parentheses. Let's see, this a 1 over a squared, that's just going to subtract 2 from the exponent, so it becomes this. And then this t minus 1 is like this. And we can now use this formula because we have that exact form here. This implies that this is equal to this, where our new t is actually 2 over t plus 1. So 2 over t plus 1. And this is 2 over t plus 1. Okay. Well, this can come up top like that. Great. Okay. So this is equal to this. So we can just put this right here. And then we'll notice that this t plus 1 and this t plus 1 cancel. We'll just put that 2 right there. And that should be correct. And now let's check it. So we'll paste that. And we'll paste this. And 1 over 3 pi e. Okay, and we'll have a equal to 7. All right, they match. Let's just vary our a a little bit, and let's vary our t a little bit. We'll say it's 1/2. Yeah. Okay, so that's true. So this is true. All right. So now we're almost ready to find an expression for this. All right, so our f of t is equal to this, which is actually equal to 2 separate integrals. We can split them. It's going to be equal to this integral minus this integral, right? Now don't forget, this is a constant. It's a divergent constant, but it's a constant nonetheless. Okay, so let's see. Now let's use this formula. This is almost the exact same thing as this, except our a squared is -1. So we will let a squared equal -1. That means a is equal to the square root of -1, which is equal to. Okay. So let's see. Let's see what happens if we plug in a is equal to I. Or no, I'm sorry. Now a is equal to I, we get minus 1. And then we get I to the t minus 1. And that's it. Yeah, because we just let a equal I. All right, so that means that is equal to that. Great. Okay. So let's replace it. This is equal to this. All right. Great. So now we have a nice expression for f of t. Of course, this is divergent. This part is not necessarily divergent, depending on what you pick for t. It's going to work out, though. So let's see. We actually want f triple prime of t, right? All right, so let's take a first derivative. F prime of t is going to be equal to the derivative with respect to t of this. But the derivative with respect to t of this part is going to be 0, so it's going to drop out. So we're just going to get the derivative with respect to t of this. All right, let's bring out our constants. Let's be careful, though. Let's bring this I to the t minus 1 over here. We get 1. And then we can bring a pi over 2 outside. And what else can we bring outside? We can bring, don't forget, I to the t minus 1 is I to the t times I to the negative 1, which is I to the negative 1 is in fact a constant. So it's just this. And we can just write that as pi over 2i times the derivative with respect to t of this. So let's do the work. So f prime of t is going to be equal to, now what we're going to get is a quotient rule. We're going to get low d high minus high d low over the low part squared. Okay, so we're going to get this squared. In fact, let's distribute this pi in here. So we're going to get pi t plus pi. And then let's split that into two separate fractions. So we're going to get plus pi over 2. Okay. Well, sine of x plus pi over 2 is just cosine x. So we can just write this as cosine of this thing. All right, so we're going to get cosine squared of pi t over 2 in the bottom. All right, now our low d high, that's d dt of I to the t, minus I to the t times d dt of our lower function. All right, let's figure this out. Well, this is just a constant raised to our variable of differentiation. So we're going to get I to the t times natural log I times natural log I. All right, and then the derivative with respect to cosine is negative sine. We'll use that negative, bring it all the way out, and then times d dt of sine of, I'm sorry, pi t over 2, which is just times pi over 2. Okay. And now let's see, what can we do? This is going to get really nasty really, really quickly. So I hope you can see we can actually do this. We can actually do this. Um, but it's going to be very difficult to not make mistakes during this integration. So what I'm going to do is I am actually going to use an integral calculator. We need the third derivative with respect to t of this. So I will be right back. I'm about to plug it into an integral calculator, and we'll just get our f triple prime of t that way. I'll be right back. All right, I'm back, and this is our expression. Now, it is extremely long, um, but you could do it if you had to. Look at how long that expression is. This is our f triple prime of t. I'll go through it a little bit slower. But some nice things are going to happen. That's it. That's f triple prime of t. But, and that we're almost done. F triple prime of 0 is equal to I. So, I is equal to f triple prime at 0, which is equal to this, where t is equal to 0. Now, let's watch what happens when we actually let t equal 0. Okay. So, if t equals 0, this is just a 1. Cosine cubed of pi over 2 is 0. So this entire expression drops out. And this is a lot of this is going to be happening. All right. Now, let's take a look at this expression right here. It contains a cosine. It is multiplied by a cosine function. That cosine function, if we let t equal 0, we get cosine pi over 2, which means this entire thing goes away. Again, we have another product that involves taking cosine of pi over 2. Goes away. All right. And now let's see. If we let t equals 0 here, we get sine pi over 2. That's nice. That's just 1. So that's not that bad. Okay. Let's see. Where's the rest of our t's at? Okay. Our t is going to be 0, so we get to the negative 1/2. All right, and if our t is 0, this is going to become sine of pi over 2, which is, of course, 1. So that really simplified down. That really, really simplified down for us. And now we got a little bit more work to do. All right, let's rewrite negative 1 as e to the I pi. Everywhere we see a negative 1, we're going to put e to the I pi. E to the I pi. Now we're almost done. We have to be careful. So let's bring this cubed out. We're just rewriting it. We're writing that as, instead of natural log cubed of that, we're writing natural log of that all cubed. Okay. Now what can we do? Well, let's see. Natural log and e cancel out to give us just an I pi right there. Also here, that cancels out to give us an I pi. Great. Okie dokie. Let's see. This is I cubed times pi cubed. So this is I cubed times pi cubed. Let's see. This is a pi times a pi, which is pi cubed. Okay, and we're going to bring that I, that's 3I. All right, I cubed. Well, let's figure out what that is. I squared is negative 1, so we'd get negative I. Negative I, and I'm being very, very careful here. All right. Let's switch this. Let's put this over here. Okay, so now we have 3I pi cubed minus I pi cubed. That's 1 I pi cubed. So this is just going to be a total of 2 I pi cubed. Okay. E to the I pi. Let's see. Let's distribute let's distribute this inside. So we're just going to get a e to the negative I pi over 2. E to the negative I pi over 2. Okay. Well, let's put that in the denominator as an e to the I pi over 2. E to the I pi over 2 is famously I. I cancels with I. This pi distributes to become a pi to the fourth, and this reduces to pi to the fourth over 8, and we are done. And just to finish it up, let's go all the way up to the top to find our original integral. Put it here, and then right underneath it, put that there, and that is the answer. So, my longest video ever, clocking in at just over an hour. I hope you guys watched the whole thing and enjoyed it, and we will see you next time.